Hi, in this section we're going to talk about dividing a proof into cases. When we are proving something, you can sometimes state something into multiple cases. You want to divide a situation into cases where you can exhaust all possibilities, and then you start breaking all those and showing that the statement is going to follow in all the cases. Some important requirement here is that all the cases must be exhaustive, so you need to cover all possibilities when you're doing cases, and that the cases must be mutually exclusive, so you don't have any overlap into the cases. Also, you need to prove each of these statements separately. Don't confuse proof by cases with try an example. An example's not going to be a proof. And your cases divide the domain into subcategories, and you need to prove each of them completely. So let's see an example of that. First than anything, let's talk about parity. So the parity of an integer is referred to whether the integer is going to be even or odd. Two integers have opposite parity if one is even and the other one is odd. Now, consecutive integers are integers where one of them is one more than the other. So, as a brief example, we have n and n plus 1. Those are going to be consecutive integers. Now, the theorem that we can use for the example is any two consecutive integers are going to have opposite parity. So pretty much one of them is going to be even, one of them is going to be odd. Let's go with the proof. So first, let's pick n to be any integer. Then the consecutive integers are going to be n and n plus 1. Now we need to show that one of them is even and the other one is odd. Of course, we need to break this into cases because n can be even or odd. So we need to consider both possibilities. So first, let's go with the case where n is even. So notice that here our assumption is n is even. And by definition of even, we're going to say that this is a k so that n is equals to k. Now, the consecutive is going to be n plus 1, but then that's going to mean that n plus 1 can be represented as 2k plus 1. And by definition of odd, that will mean that n plus 1 will be odd. Hence, that's going to be that if n is even, then n plus 1 is odd. Now we need to cover the second case, which is the case where n is odd. If n is odd, then we're going to have that this is the k, so that n can be represented as 2k plus 1. But then, if you consider n plus 1, then we're going to have that is 2k plus 1 plus 1. So we're going to have 2k plus 2, which we can factor the 2 out, and we can see that as 2 times k plus 1. Now, since k plus 1 is an integer, by definition of even, n plus 1 is going to be even. Now, notice that we cover all cases, and we have here that n and n plus 1 are going to have opposite parity in both of those cases. Since the cases are exhaustive, every integer is going to be even or odd, then any two consecutive integers will have that opposite parity. Now, it's important to check we divided into case based on the parity of n and prove the statement in each of cases to cover all possibilities. This is something that we always need to do. Now, let's introduce the quotient remainder theorem. The quotient remainder theorem is essentially one way of proving what you will call the long division. So just to make a quick drift here into what will be the long division, normally you are dividing a number n by a number d, and then you have that d is in n q times, and then you have a remainder that is r. That is how regular long division works. So for example, for let's not go with 4 because it has no remainder. Let's go with 5, right? 5 can be divided by 2, and it's 2 times, and the remainder is 1. Well, the proof of this will be saying, oh, okay, notice that n can be seen as q times d plus r. So you multiply how many times d is in n, which is q, so q times d plus r, and so you have this representation, q times d plus r. In this case, with the numerical example, we have that 5 can be represented as 2 by 2 plus 1. Okay? So now let's go back to the theorem. So the quotient remainder theorem is saying that for any n and any positive integer d, there's going to exist number q and r, so you can represent as n as d times q plus r, and the remainder is going to be a number that is between 0 and d. Of course, we're using d as how many times q is in n, so the remainder gotta be less than that. Okay? Now, yeah, so we're dividing n by d, and so the remainder gotta be less than d, otherwise we will have another instance of d in. Okay, so now here in terms of terminology, we can say that n is in this case the dividend or the number being divided. D is the divisor or what we're dividing by. In this case, I'm doing n divided d. Q is going to be the quotient, which is going to be the resulting number, and R is going to be the remainder, which is what is left. Okay. So one of the critical constraints is going to be, of course, that the remainder is less than d, and is also non-negative. This is also a unique representation. For any n and d, there's going to be just one pair of q and r that satisfy these conditions. Now, some notation that I can use when I'm talking about quotient remainder is the mod notation. So for example, the n mod d is going to give me r, or this means n mod d equals r, which is going to give me immediately the remainder. So n mod d is just giving me the remainder of the division of n with d. Now, if I just do n divided by d, that's going to give me q, which can also be seen as n div d equals q. So there's two notations here, the mod, which gives me the remainder, and the div, which gives me the quotient. Now let's see some examples with this. So first, let's find q and r so that I can find the division between 7 and 2. So essentially I'm checking, well, how many times 2 fits in 7, right? And so you know immediately that, well, 2 and 7 is going to have 3 times. And so it's going to have a remainder 1 because I cannot fit another 2. So it's 2 times 3 is 6 plus 1, 7. And so I can do this representation. So my remainder here is 1, notice, less than 2, which is how I was expecting. So I find out that my q and r are just going to be 3 and 1. And they hold all that we were expecting. Therefore, here 7 divided by 2 is going to be 3, and 7 mod 2 is just going to be 1. Now, for the second example, I'm going to find q and r so that 38 can be seen as 3q plus r, with r being a number between 0 and 3. Now, in this way, we represent 38 as 3 times 12 plus 2. Here, the quotient is going to be 12, and the remainder is going to be 2. Once again, notice that the remainder holds my hypothesis, and the remainder is less than 3. And once again, we have what we were expecting, that is 38 divided 3 is 12, and 38 mod 3 is equals 2. Now, a third example, let's take a negative number now. Let's find a q number and an r number such that minus 11 is equals 3 times q plus r. Of course, r is going to be a number between 0 and 3 given our initial condition. This is going to be a bit trickier because n is negative, but then it's very likely that I just need to use a negative number. Notice that r gotta be a positive number. So that means that I always gotta think in a number that is gonna fit, but is gonna be positive here. So we try with -4, and that actually is gonna work since 3 by -4 is -12, and then we just need to add 1. And so -12 plus 1 is -11. Indeed, we can check 1 is a number less than 3, so it holds the condition for our remainder. In Q, we don't have any restrictions. It can be a negative number, or quotient is going to be here -4. Therefore, -11 divided 3 is going to be -4, and -11 mod 3 is just going to be 1. You got to be careful here. You can have -11 represented as 3 times -3 with -2. However, this is not the correct representation for this theorem because -2 is a negative number. And by definition, we decided that the remainders should be negative. Okay? Now, applications of this. We can apply all this for cycles. So we can use this modular arithmetics that we're defining, so we can see patterns and we can see when things repeat. So for example, on Monday, a friend says that they will meet you in 31 days. So what day of the week will that be? And so the days of the week repeat every 7 days. So we can divide 31 on 7 days and see how many is that going to be and what is the remainder. So in this case, we'll have that 31 can be represented as 7 times 4, which is 28, plus 3. So 31 mod 7 is going to be 3, which is a remainder. And starting from Monday, which will be day 0, we go forward 3 days. So it will be Monday to Tuesday to Wednesday to Thursday. So the answer here will be Thursday. You will meet again in a Thursday. Now, let's talk about forms of integers. So if we use d equals 2, then any integer can be written as n is equals 2q or 2q plus 1. Essentially, we're divided by 2, right? So the remainders have to be less than 2. So there's only 2 numbers, 1 or 0. So this means that if we're going to represent any integers as a multiple of 2, it gotta be 2q or 2q plus 1. Now, this is gonna give me any integer can be from the form even or odd, essentially. Now, but we can generalize this idea to other numbers, so we can go with 3. So now any integer n is gonna be written as 3q, 3q plus 1, or 3q plus 2. And it's essentially the same idea. This plus 0, plus 1, plus 2, because those are the remainders that we can use. With 4, then we start increasing. At this point, you probably realize what the game is. N can be written as 4q, 4q plus 1, 4q plus 2, or 4q plus 3. Now, the general pattern is that for any positive integer d, every integer can be written in exactly one of the form n is equals dq, dq plus 1, dq plus 2, up to dq plus d minus 1, since that's what the remainder will allow. This is powerful for proof by cases, although it's a lot to prove. So when we need to prove something about the integers, we can always choose an appropriate divisor d that it can work for what we're trying to prove, divide into d cases dependent of the remainder that we're choosing to use, and prove the statement in each of the cases. So one example of this will be prove that the square of any integers is going to have the form 3k or 3k plus 1 for some integer k. Now, to prove that, we pick any integers. And so by quotient remainder theorem, we can say, well, let's go with multiples of 3. So n is going to be either 3q, 3q plus 1, or 3q plus 2. Why did we decide to prove with d equals 3? Well, because we want to show that they're multiples of 3k or 3k plus 1. Now, what we're going to do, of course, is we're going to pick any of these cases, and we're going to prove that they have this shape. So first, we start with case number 1. N is 3q. We square that, and so we're going to have 9q squared. But 9q squared can be seen as 3 times 3q squared. Or if I call 3q squared some number k, I can see n squared as 3k. So this is so far so good. We're proving what we wanted. Let's go with the second case. N is 3q plus 1. Now, if we square that, then we have that this is going to be from the binomial square form, 3q plus 1 square. And so squaring that, breaking that binomial, we're going to get that this is 9q squared plus 6q plus 1. Remember, first one square plus 2 times the first one by the second plus the second square is going to give me this. And notice that from this part, I can kind of factor a 3. So I can see this as 3, this number plus 1. I can make this k, and since that's going to be an integer, because q is an integer, and so we're going to have that n squared is from the shape 3k plus 1. Now, the final case, if n is 3k plus 2, we do the same thing. We square, we break the binomial square. And so notice that we can pick this entire piece, factor 3, leave this one out. And so we're going to have that this 3, this number plus 1. And so if we make this k, once again, we have that n squared is from the shape 3k plus 1. In conclusion, all 3 cases of n squared are going to have the form 3k or 3k plus 1. Since this is covering everything, since every integer has one of these forms, then the proof is complete. Notice that n squared can never have the form 3k plus 2. Now, let's talk about some common mistakes that can happen here. So you are thinking that cases are examples. That's not something that happened. Like, for example, let n equals 2, which will be an even case, or n equals 3, an odd case. When you're just given values, that's not enough to prove. You gotta prove something in the way like, suppose n is even, then n is equals to k for some integer, and same for the odds. You gotta cover all the possible integers of a symbol type, not just one example. You also need to cover all cases. When you're divided by 3, you need to get all the remainders, 0, 1, and 2. Missing a case is going to get your proof to be incomplete. Well, also you're using the quotient remainder theorem. Make sure that you're not using negative remainders, because otherwise it doesn't fit the theorem. And although you might get a good representation or a representation of the number, it's not going to be the representation that is given by the theorem. Now, it's very important not to confuse regular division with some of the stuff here. You have many things that are working in terms of the regular division, but you're getting pieces. So, for example, n mod d is giving you the remainder. N dip 2, or this symbol, is just giving you the integer quotient. It's not giving you the parts. Also, be careful not verifying that you get a piece is an integer. For example, if you're writing n squared is equals 3k, you must verify that that k is an integer. You gotta show and say why that is an integer, if it's built from integer operations or on integers. Also, do not forget the uniqueness on the quotient remainder theorem. For any n and d, there's just one pair that is going to work. For example, we can have 7 is 2 times 3 plus 1, and also 7 is 2 times 2 plus 3. This is going to violate that the remainder got to be less than what you're dividing for. You can have multiple representations for the number, but it won't be the representation of the quotient remainder theorem. So now, in summary, we discussed the proof by case, how to divide into exhaustive cases and prove each of them, the quotient remainder theorem for integers n and d, and all the form of integers that an integers can have when it's divided with an integer d, and the remainder that can take numbers from 0 up to that number d minus 1. In terms of parity, consecutive integers can have of opposite parity, and cases are not example. You need to prove for all integers each of the things that you're doing. Okay, next we're going to talk about indirect argument, contradiction, and contraposition. But for now, let's take a look at some more examples on the class note examples video.